6.4 Binomial coefficients and identities. A binomial is something with two terms, like x plus y or 3 minus a. So just two things connected with an addition or subtraction. If we take powers of binomials, what do we get? So what does that look like when we expand it out? Well, the first power of x plus y looks like this. The second power, so that means x plus y times x plus y. So if you remember foiling, you could FOIL this out. The first, inner, outer, and last combinations. Then we get two like terms, so xy is the same as yx, so we get two of those. Okay, so combining those like terms, and the answer is x squared plus 2xy plus y squared. That's the second power of x plus y. How about the third power? Okay, so multiply the second power by another x plus y. Yeah, we can't FOIL it anymore, but it's more like distributing, so we get x times each of these, so that gives three terms, plus y times each of these gives another three terms. Okay, so 6 combinations. And there are also some like terms here. So we have an x squared y, and this is another x squared y. So 2 plus 1, 3 of those. And then xy squared. So 1xy squared plus 2xy squared, that's 3. 3 of those. So for the third power of this binomial x plus y, we can write it 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Okay, and these numbers, these are called coefficients, 1, 3, 3, and 1. Is there a formula for these coefficients? Yes, so these turn out to just be these combination numbers that we looked at last time. And in this context, yeah, we usually write them like this. So parentheses with the n above the r. And these are called binomial coefficients. So these are the coefficients, the numbers that show up when you take powers of binomials. And yeah, so it's nice we have formulas for these combination numbers, these binomials, binomial coefficients. The way to read this is n choose r. So n choose r is equal to n times n minus 1 dot dot dot. So multiply r numbers, r integers, starting with n and going down on the top, and then on the bottom it's r factorial, so r times r minus 1 down to 1. So that's the easiest way to compute these. Yet also, this is a factorial formula. Okay, so this, you can see that's good news. So instead of doing all this complicated distribution for higher powers, we can just write down the answer in terms of these numbers. And yeah, also note this kind of special case. So these numbers on the end are always ones. So 3, choose 0. Yeah, it's a bit confusing. So yeah, how many ways to choose 0 things from 3 things? Well, it's always going to be 1. Choosing 3 things from 3 things, yeah, that makes more sense. That is 1. Okay, so just these 2 cases. So if you have a 0 down here, so this binomial coefficient is 1, and that does make sense from the factorial formula. Remember, 0 factorial is equal to 1. And n choose n, that's also 1. Okay, so example 1 here, what is the coefficient of x to the power of 5, y to the power of 2 in the expansion of x plus y to the power of 7? Alright, so yeah, so this example kind of explains where the formula comes from. So x plus y to the power of 7, so we have 7 of these factors, x plus y. Okay, now when you multiply this out, so each factor contributes either an x or a y to each term. So to get an x to the power of 5, y to the power of 2, then we'd have to choose x's from 5 of the products and y's from 2 of the products. Okay, there are lots of ways to choose 5 x's from these 7 factors. How many ways? Well, it's 7 choose 5. It's this combination number, this binomial coefficient. Alright, so the coefficient we're looking for is C7, 5, or 7 choose 5. So start with 7 on the top and go down. So we need 5 numbers here. 5 factorial on the bottom, and as usual we can cancel so that's just 21. Alright, so when you multiply out this big product, you get lots of terms. But in the middle you get 21 x to the power of 5 y squared. Alright, so this was the coefficient we were looking for, just 7 choose 5. And remember that symmetry we saw before, so 7 choose 5 is equal to 7 choose 2. So we could have used this binomial. Right, so yeah, it doesn't matter which of the powers you use, 5 or 2, for this. Okay, so we're not writing out the full expansion, just this piece. All right, so this is just an example. So what is the general result? Okay, so this famous theorem called the binomial theorem. So if you have x plus y to the power n, where n is any non-negative integer, then it expands into this sum. So it's n choose 0 x to the n plus n choose 1 x to the n minus 1 y to the 1. Okay, so this pattern continues, and so n choose 2 x to the n minus 2 y to the power 2, and all the way down to this last term, n choose n x to the power n minus n, so that's x to the 0, that's 1, times y to the power n. Okay, so you see the pattern in summation notation, so using an index j that runs from 0 to n. So it's n choose j times x to the power n minus j, y to the power j. Okay, so you can see the powers of x and y, they always add up to n. And we saw that in our example. So for the 7th power, 5 plus 2 equals 7. So those are the only kinds of terms that are going to show up. Alright, so it looks complicated, but this is just what we're doing. And we saw an example when n equals 3 earlier, just with these coefficients. So another example, use the binomial theorem to expand x plus y to the power of 5. Okay, so when n is 5, then we need 5s on the top, and we're getting all these terms where the sum of the two powers adds to 5. Okay, so 5 choose 0, x to the power of 5, y to the power of 0. 5 choose 1, x to the 4, y to the 1. 5 choose 2, x cubed y squared. Yeah, so just to keep track, yeah, so if you have a 2 down here, then yeah, one of these powers has to be 2. And all the way to 5 choose 5, x to the power of 0, y to the power of 5. Okay, then work out these coefficients. 5 choose 0 is 1, so yeah, whenever you have a 0, you get a 1. And that's equal to 5 choose 5. if I choose 1, that's 5 over 1 equal to 5. And that's the same as 5 choose 4. 5 choose 2, so now we need two numbers starting with 5 on top and 2 factorial on the bottom. So 20 over 2, that's 10. Okay, we're just using this symmetry. Remember, n choose r is always equal to n choose n minus r. Okay, so this gives us 1 here, 5, 10, and then symmetrically 10, 5, and 1. Alright, so this is the expansion we were looking for x plus y to the power of 5. Okay, so just written again, we get this identity. Okay, so this is true for every real number x, every real number y. Okay, we get this pattern of binomial coefficients 1, 5, 10, 10, 5, 1. And so you can play around with this. So since this is true for every real number x and y, you could put in numbers as examples. So for example, when x is 1 and y is 1. Okay, so we're just putting in 1s here. Well, 1 plus 1 is 2, so we're getting 2 to the power of 5 on the left. And then all these powers of x and y just turn into 1s. So this is saying 32 is equal to this sum, 16 plus 16. But it's also saying, if you add up all the binomial coefficients, you get a power of 2. Okay, and the power is coming from the top number. Alright, so that's a nice pattern. Another case, if x is 1 and y is negative 1, so make a minus here. So 1 minus 1, that's 0. 0 to the power of 5, still 0. So now we have an alternating sum. The powers of x are still 1, but the powers of y alternate. So odd powers are negative, even powers are positive. Okay, so if you write down the binomial coefficients like this, alternating the sign, then you always get 0. Okay, there are more patterns you can look at, so just so these are really special cases of the binomial theorem, so just putting in different numbers. So yes, in general, we get these two formulas. So if you add up all the binomial coefficients with top number j, with top number n, you get 2 to the power n. And if you make an alternating sum with the sign switching, all the binomial coefficients with top number n, then you get 0. Okay, we'll see that pattern again. Okay, but going back to our applications of the theorem, example 3, what is the coefficient of x to the power 4, y to the power 5 in this more complicated binomial power? Okay, so the power is 9. Instead of x plus y, we have 3x minus 2y. Okay, but it's still a binomial. It's still sum or difference of two terms. Okay, so we can write it like this. So instead of an x, we have 3x. Instead of a y plus y, we have plus this quantity, negative 2y. Okay, so it's like we're substituting. So replace all the x's with 3x. Replace all the y's on both sides with negative 2y. And here n is 3, n is 9. Okay, so we get this big sum, but yeah, we're just interested in the 4th power of x and the 5th power of y, so we just need these pieces. Yeah, we could have used 9 choose 5 here, but that's equal to 9 choose 4. It doesn't matter. Yeah, it just has to match one of these powers. Okay, so instead of x, we have 3x to the power 4, and here we have negative 2y to the power 5. Okay, so remember the rules for exponents, so the quantity 3x to the power 4, that's 3 to the power 4 times x to the power 4. And this breaks up as negative 2 to the power 5 times y to the power 5. Alright, yeah, so this is more complicated. We have some extra numbers, but this is the coefficient we're looking for. So we have the binomial coefficient piece, 9 choose 4. So that's 9 times 8 times 7 times 6. So 4 numbers starting with 9 divided by 4 factorial. Again, it's simpler to look for cancellation. Okay, so we're multiplying all these numbers together on top, multiplying all these numbers together on the bottom, so we can cancel common factors. Cancel the 3 out of the 6 to get 2. So what's left? Yeah, 9 times 7 times 2. Yeah, 63 times 2, that's 126. So that's this piece, 3 to the power 4 is 81. And negative 2 to the power 5 is negative 32. And multiply those together. So the answer, the coefficient we're looking for is this number. Okay, so yeah, so the piece of this power, when you expand it out, the piece that contains x to the power 4, y to the power 5 is multiplied by this number. Alright, so yeah, so we're just using this binomial theorem. You can substitute anything, more complicated things for these x's and y's. Okay, in the book. Yeah, the binomial theorem. Again. Example 2. What is the expansion of x plus y to the power 4? Okay, so it's the same pattern. This time we have 4's on top. Okay, and then working out these binomial coefficients, we get a 1, a 4, 4 choose 2, that's 4 times 3 over 2 times 1, that's 6, 4, and 1. And again, for a fourth power, we expect that that's the two powers of x and y to add up to 4. And we can see that here. So this is the answer. So yeah, this is called an expansion. So this is the expanded version of this power. Example 3, what is the coefficient of this term in the expansion of x plus y to the power 25? Alright, so that's the biggest power we've seen so far. Okay, so yeah, we will get a term like this because 12 plus 13 equals 25. Well, the coefficient we need is 25 choose 13, or it's the same as 25 choose 12. It doesn't matter which power you use, but the top number has to be 25. Okay, and then yeah, this, so you'll need a calculator to work this one out. 5,200,300. Okay, and a similar one, but just with, instead of x and y, again, like we did before, now we have 2x and minus 3y. Okay, so yeah, I guess we do have to be a bit careful here. So this is our formula from the binomial theorem. So yeah, so here, yeah, actually it doesn't matter. If we choose 12 or 13. But yeah, so this time it's, so instead of x, we have 2x, so we're going to get a 2 to the power 12. And instead of y, we have negative 3y. So we're going to get a negative 3 to the power 13. So that's an odd power of a negative number, so that makes the whole thing negative. And yes, so maybe it's easier just to leave it like this. So this is the answer. Yeah, you could get a very big number out of this since these powers are so big. Alright, so next topic. So now we're looking at some more patterns for these binomial coefficients. If you add two consecutive binomial coefficients, you get another binomial coefficient. And so n choose k plus n choose k plus 1. Okay, so the same top number and consecutive bottom numbers. That's equal to n plus 1 choose k plus 1. Okay, so the top number went up by 1, and we have the same, the biggest of the two on the bottom goes here. So this is called Pascal's identity, after a French mathematician, Pascal. We can prove it using our formulas. So remember, we have n choose k in terms of factorials. So n choose k is n factorial over n minus k factorial times k factorial on the bottom. Replace k by k plus 1, we get this. Okay, now we want to add these two together. Okay, we're adding fractions, so we want a common denominator. So we have a k plus 1 factorial here, and a k factorial for the first one. So it's easy to go from k factorial to k plus 1 factorial. Oops. Just multiply by k plus 1. Okay, so k factorial times k plus 1 is equal to k plus 1 factorial, and I have to include that k plus 1 factor on the top. Okay, and also for the other piece, we have n minus k factorial here, and we want to make this into n minus k factorial, so this has to be multiplied by n minus k. Okay, so we're multiplying by n minus k, top and bottom here. Alright, so now we have a common denominator. Now we can just add the tops together. So we have n factorial times k plus 1 plus n minus k. So we're combining two steps here. So it's just this plus this, and then factor out the n factorial. And then this whole thing simplifies, so k plus 1 plus n minus k. All those two k's cancel. And so it's just n factorial times n plus 1, and that's n plus 1 factorial. Alright, so that's so now we can recognize this is n plus 1 choose k plus 1. So that's the proof, just using formulas for Pascal's identity. There is maybe a more enlightening proof in the book using choosing arguments. Comparing choosing from a set of size n to a set of size n plus 1 as the subset increases. Okay, but we can at least check the formula is good. Example 4. Check that 8 choose 3 plus 8 choose 4 is equal to 9 choose 4. Okay, so that's a special case where n is 8 and k is 3. Well, 8 choose 3, that's check, that's 56. 8 choose 4. Okay, so how many ways to choose 4 things from 8 things where you don't care about the order? 70 ways. And 9 choose 4. Check, that's 126. Okay, so the formula looks good. Checks out in this case. Okay, so that's Pascal's identity. Let's take a look at Pascal's triangle next. Alright, so if you draw the binomial coefficients and make a triangle like this, so starting with 0 choose 0, well that's 1. Okay, then increase the top number to 1. So 1 choose 0, 1 choose 1. We get 2 1s. Then for this row, with 2's on top. So these are the numbers that come out if you have x plus y to the power 2, x plus y to the power 3. You get these numbers. All right, so you could keep going, make a bigger and bigger triangle, just using more of these coefficients, but we're stacking them like this, kind of symmetrically. And why is it nice to look at it like this? Well, so the way we're stacking them, so if you look at the nth, well, the row with n's on top, so n choose k and n choose k plus 1. Well, if you add these two, then by Pascal's identity you get the binomial coefficient 1 below in the middle. Okay, and you can certainly see that here. So 1 plus 1 is 2. 1 plus 2 is 3. Also 2 plus 1 is 3. Okay, so this is really, you can see Pascal's identity here. 2 choose 1 plus 2 choose 2 is equal to 3 choose 2. Alright, so here's a row in Pascal's triangle, so 2 rows down from this one. Okay, so if I give you a row of Pascal's triangle, then it's easy to get the next row. Okay, so it always starts and finishes with 1s, and then just add these two to get 6, add these two to get 15, put it in the middle. 10 plus 10 is 20. Alright, so just from one row of Pascal's triangle, it's easy to get the next row. And yeah, so that other pattern we noticed, if you add all the coefficients, if you add all the numbers in one row, you get a power of 2. So yeah, we saw if you sum all of these, we saw earlier it's 2 to the power of 5, 32. And if you add all of these, well, 1 plus 6 is 7, 22, 42, 42 and 15 is 57, plus 6, 63, plus 1, 64. Oh yeah, so that's 2 to the power of 6. Yeah, so summing these the rows in Pascal's triangle, you always get a power of 2, and it's always this power of 2. And we can see more of the triangle in the book. Yeah, here's another way to write Pascal's identity. Instead of k, they had k minus 1, but it's the same identity. Yeah, so here's more of the triangle. Yeah, we stopped here. So here are the next rows. Okay, so again, every number is the sum of the two above it, to the left and to the right. Alright, so let's see, Pascal's triangle, it goes forever. And here is Pascal. Yeah, he worked on lots of things, yeah, including probability. We'll look at next. Alright, so that's more information on binomial coefficients.